distance between A and B and the average time it takes for sound to travel from A to B, B to A. So what is the advantage of having this equation? The answer is that the C, or the sound speed, depends on the temperature of water, salinity, and depth of water. So we are in very shallow waters, and I assume that the people here have some basic knowledge about the sound speed. So if you remember the Medvin equation for sound speed, the depth effect can be neglected in shallow waters, and especially if you are in a freshwater river, the salinity is 0, so you can actually have the temperature of water along this path. On the other hand, you're going to have the UM, or the velocity average over the path. Again, I stress it is not the flow velocity itself, which depends on the delta T, the average sound speed, and inverse of the distance between these two. So as long as you have directional transducers, which means that they have one beam and they don't scatter all the sound, you're okay. But if you go to somewhere that there are some gradient of sound speed, then this path is not going to be straight, which means that you're going to have a lot of errors in your measurements. So to solve this problem, we actually started an innovative acoustic system, which is called Fluvial acoustic tomography. The idea of using sound to probe the state of ocean has been around since 1978, when Mark and Wu proposed to use the sound for measuring the temperature and velocity in the ocean. But don't forget that in the ocean, the water is very deep, so if you have a source or receiver, there's very, very low chance that your sound waves are going to interact with the surface of the ocean or the bottom of the ocean. So the problem starts when you come to the shallower waters. Why? Because when you're using, say, 5 kilohertz sound speed, you can have very strong sound. But when you go to the shallower waters, because the depth is quite limited, you have to go on higher frequencies, and at the same time, because it's shallow, there's going to be a lot of interactions between the surface of the water and the bottom of the bottom boundary. So each time that sounds interact with each of the boundaries, some of it is going to be absorbed, or let's say it's been attenuated. It gets attenuated. So in the shallow water, there is this delicate balance between the sound frequency, the energy it can carry, and the sound attenuation. So Conoco in 1998 invented the CAT system, or Coastal Acoustic Tomography system, and then Kawanishi set one step forward for using the CAT. The CAT is the backbone actually of the FAT, or the Fluvial acoustic tomography, but it can be used in the shallower waters. The difference, as you can see, as you go to the shallower waters from the bay to the say rivers, the acoustic frequency is going to go higher and higher. But the problem with the system, the initial system of the Fluvial acoustic tomography, was that it could be operated with only one acoustic path. We're going to discuss that, why it is important for us to be able to incorporate more than one path in here. So I got this system looked like this. It was in prototyping stage. It has a 1 Hertz frequency GPS clock. The GPS had a lot of problems, so there was sometimes the shift, 1 second shift between the two stations. And let's not forget that we are talking about sub-millisecond timekeeping. So 1 Hertz was very large and very rough. Also, the housing for the transducers, this is a transducer inside this. And there's an amp in here. There was a lot of leakage in these housings, and the connections are very weak. Even by pulling out it hard, you could damaged the cables, and the amps were very primitive. They were working, but yeah, there were a lot of wires running around the system. And if you've ever worked with analog system, you know that each piece of cable acts like an antenna and introduces more noise to the measurements. So the sound to noise requirement for the system, so the data to be meaningful, the signal to noise ratio was about 10, 12, or even 15 decibel. So anything below that had to be discarded. So in cooperation with our technicians, with the Acoustical research, we built the system, but actually only the outside was looking good, and I was not satisfied. So I started my own modifications of the system. I replaced all the wires and I put them in one PCB. So I reduced the length of the wires considerably. It means that the noise in the system was reduced considerably, and then the housings were redone and the connections were redone, the amps were redone also, and then most importantly, the GPS clock was also replaced by a 10 megahertz very robust GPS clock. This GPS clock is used both for timekeeping and also calculating the frequency of the sound. So it meant that we have the accuracy up to 6 digits using a 10 megahertz GPS clock. And then we added a Raspberry Pi. A Raspberry Pi, for people who don't know, is a like credit card size computer. So it allowed us to connect the system to a cellular network and send the data to a cell phone network at the same time. It meant that you can actually measure the flow velocity in real time. But I would stress that none of these improvements could be done without the work of Professor Goda, or Goda Sensei as we call him, Noriaki Goda at Hiroshima University. So what are the features and advantages of FET? Let's start with that we modulate the signal with an M sequence. Have you ever thought that why an area is covered with one cell phone tower, and when someone calls, only your cell phone starts to ring? The answer is that because the signal is modulated, and it is only your phone that has the key. So there might be, say, 1,000 people in the area, and the antenna sends the signal to everyone, but only this is you who pick up the phone, because this is you who have the key to the code. So we actually do the same thing, and it allows us to distinguish between the two sounds, the different sources, but the exact arrival time. And also it increases the correlation between the pulse that is sent and received. So we're going to have a very sharp peak, which allows us to estimate the arrival time with very high precision. And the other thing is that it has higher frequency. The higher the frequency, the more the resolution in the data. And also that you can have very small separations, because say you're using 1 hertz or say 1 kilohertz frequency, then the minimal distance should be at least 3 times the wavelength. It means that if you go to the higher frequencies or shorter wavelengths, then you can have a smaller separation between the source and receive. It means that you can do the measurements in rivers as wide as, say, 30 meters. And then the 10 megahertz GPS, we discussed this already, and omnidirectional transducers. If you have a directional transducers as the AVM or acoustic velocimeter, then you have to actually adjust and calibrate and actually aim the receiver. It means that here it's about 1,400 meters, 1,500 meters. If you're just off by 1 degree, then on the receiver you're going to be off by 20, almost 5 meters, which means that you're not going to receive any signal at the receiver. So you need very, very delicate calibration of the direction of your transducers, and which is very laborsome and tedious. And it is not only doing it for once, but you have to maintain it as long as you are actually using the system. So most of the time people just abandon it, and one of the reasons that AVMs are not used anymore is that it was really hard to maintain them. And the other problem was that because the sound actually travels along one straight line, then you have to have another measures of velocity. It actually is an index velocity because you're measuring the velocity only along one line, and then you have to have like an ADCP to measure the discharge, and then have a stage, or in this term like AVM velocity discharge relationship. It's almost like a rating curve. And the other thing about, and the other important feature of the FAT is that, oops, I'm trying to go to the previous one, is that, I'm sorry, is that it is installed far from the deepest part where the currents are strongest. So imagine you have a flood coming. You're not going to risk any lives because it doesn't need any operator, and at the same time is far from the strong current. So there's a good chance that you can capture the flood, and we all know that the data on flood is very scarce nowadays. And it's very cheap to maintain. As you can see, it runs with a small, say, car battery or boat battery, and a small solar panel. It runs forever, better say. Now, let's get back to the issue, the problem of using only one crossing path. So if you just have one crossing path, you're going to resolve the velocity along the path. So it means that you don't have the flow direction itself. What you're going to have is going to be the velocity magnitude and a sign. It's going to be positive or negative. Positive, say, it's going to be downstream, and negative is going to be toward upstream. So it's not very useful, especially in the estuary. So if you have one diagonal path, you can measure the current speed in rivers. It's really good. Or you can do the climate change because you're measuring the temperature, or you can use it for the hydropower plant because they introduce thermal contamination, because HPP or hydropower plant means that you're going to need a dam, and dam means that you have a small lake behind it. The lake is, the water in the lake is usually very colder than the river. So by opening up the gates to run the turbines, you're actually going to contaminate the downstream by introducing a lot of cold water. So if you have two crossing paths as shown here, then you're going to have two components of the velocity, which means that you're going to have the direction of the velocity. So it is very useful in estuaries when the direction of flow changes very intermittently, and when you want to enhance the operation of a sluice gates, or if you are a meandering part of the river where the direction of the water changes with water level, in fact. But if you have more than, say, 6 nodes, here is very simplified version, then you can actually resolve the gradient of velocity inside this area, and it's not just going to be two velocity components. So in this case, it's going to be like, it opens up a lot of applications, like for industry like tidal farms, because you have, say, 20 turbines you want to put in the water, and you're interested to know where the current is the strongest. And this is just before installing the turbines, but after that you're going to see that how the current has changed, and how the distribution of sediment transport has changed. For calibrating the numerical models, most of the circular model are not really calibrated against these in-situ data because they are not available, and most often they use an ADCP. ADCPs are point measurement instruments, or you can actually measure the advection of contaminants. Let's say you have a farm that introduces a lot of pollution to the river, then you can actually model and simulate that how this advects into the river. And the design of a spillway in lagoons, let's move a little faster, or environmental preservation, because in lagoons temperature is very important. So if you can actually have the temperature distribution inside the lagoon. You can see that there is warmer, or you have the highest efficiency. And assessing that, now we have this instrument, this new instrument. I guess the very first step is to assess the accuracy of the system. What we did, we took the system to auto diversion channel downstream of the sluice gate. Only 1/3 of the sluice gate is open, and you can see this sandbar is this sandbar. So during the high tide, cold fresh water runs along the right bank, and during the low tide, you can see that because the path is blocked by low tide, it's going to go around it. So we have 4 stations, and we did some measurements with a moving boat ADCP and some CTDs. We decided to do it during spring tides when the currents are very strong, and also we had a large amount of fresh water, so it meant that the water column is going to be well mixed. And during a neap tide and very low discharge, because we were interested to know what are the effect of the stratification of acoustic tomography. Okay, this is the spring tide. As we can see, the water column is most of the time well mixed, but as I said, the path of the track of the fresh water changes with the water water level. Here is low, here is your sandbar, so it goes around the sandbar. Here is high, so it just directly comes. And this is an extreme case of strong stratification, because the top layer is actually the seawater, it's saline, and the lower one is cold fresh water. But we can see that if we compare the velocity of fat, the red line, with the ADCP discrete measurements, the error for both direction and velocity is about ±10 degrees, which is really good. But during the neap tide, there was a totally different story, because most of the time we had very strong stratification, as you can see, and the stratification was measured by Bront-Weissel frequency in here, and this P actually coincides with this layer, as you can see here. The result, the fat result deviate strongly and significantly from the fat measurements. I wanted to know that why is the difference. So I put together a very primitive ray tracing code together, and I started ray tracing. So this is the sound, and this is a receiver. We had this the sound speed variation between the source and receiver from the CTD cast. We had, I guess, about 6 or 9 CTD casts across the river, so we had a very good measurement of the sound speed. And here we can see that if the source and receiver are not submerged into the salt wedge, then the sound ray is going to trap on the upper duct, so it actually measures the high speed flow, and it just neglects the low speed part of the cross section. As a result, it overestimates the water velocity. And here you can see these green dots. These are the ADCP dots, but I just removed this part from the ADCP measurements, from the ADCP transects, and then integrated the flow velocity and average over this area. So as you can see that the conformity is very exciting and very nice. There's a very nice conformity between ADCP and FAT in this time, which kind of proves that the FAT was only measuring the upper part of the water velocity. One solution is to take your sound, the source and receiver lower. So this is another case. If you submerge them into the salt wedge, then you're going to have the transmission and the sound traverse across the cross section. Having that in mind, that flow can be very complex in estuary. To visualize the flow, I decided to go somewhere with less vertical complexity of flow structure. So I decided to go to a shallow water, to a shallow freshwater river. Here we can see it's Gono River. I didn't want to be in a straight reach of river because a straight reach means that there are no actually distribution in water. The streamline is going to be straight, so there was no point. So I picked a reach of river that was downstream the confluence zone. Here we can see the Sidra River with very cold water. Here you can see the water was always colder and were in the right bank than comparing to the left bank. Here it was about 2 degrees colder because of the Saijo river was colder than the Boston River, and also is in the meandering part of the river, and then we have some changes in the width of the river and downstream, which means that the flow is going to be more or less complex. To provide the reference data, we also had 2 up-looking ADCPs. One was, they were quite close to the banks, unfortunately. One is at the left and the other is at the right bank. Now back to the office, how we can use these 16 paths. We had 8 stations, 4 on each side. They have to be scattered randomly, and the distance must be different from each other. And we have 16 paths, and how we can use this 16 acoustic path to visualize the flow. First step is to write the stream function using the Fourier series. You can use any other series, but here I just use the Fourier series. But keep in mind that the Fourier series are strongly periodic. So to diminish or reduce this effect of periodicity, I decided to have 2 actually domains. One is the physical domain that is defined by the acoustic stations, and the other one that is larger, I call it computational domain. So Ly and Lx are in this case I selected Ly to be double as large as the L in the physical domain. So what are the unknowns in here? Is C0, D sub 0, and the rest of the CKL, that is changes with the path, and X and Y are actually the X and Y of the systems. So this is your unknowns, and we're using actually the stream function because it reduces the number of your unknowns. Of course, you can solve and write the equations for the U and V, but you're going to end up with too many unknowns, and you should consider always that the number of knowns or the delta T across the along the path is very limited. In this case, we have 16. So how we're going to solve these equations? We have some knowns in this side on the left side, and we have the unknowns on the right side. So if I want to write it in the matrix notation, we're going to have the data, and we have the geometry matrix, which depends on the geometry of your stations and or the unknowns. So we're going to have to solve this particular equations. But remember that because the computational domain is larger than the physical domain, then you might have some streamlines that just go through the boundaries, which is not acceptable. So what you're going to do is that introduce some boundary condition. How you're going to do that? You're just going to set the velocity perpendicular to your boundary to 0. Whatever velocity, this is the normal vector at each location. So say you're going to have the boundary location here, 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 and here. So you're going to have all the velocities, set all the velocities that are perpendicular to the boundary to 0 using this. And you're going to calculate these two matrices, and you're going to end up with a general form here. I call it G M equals D. So one easy solution is to use the least squares. But the least squares are very susceptible to any outlier, which means that if you have one or two outliers, then there's a good chance that you're going to end up with the wrong answer for this equation. Remember that most of the inverse problem are ill-posed. It means that there are definitely more than one solution that can satisfy the equations. So to pick the best solution, I use the Tikhonov regularization technique. You can use any other regularization technique like archaic information like AIC, or you can use BIC, Bayesian the information, I forgot that, or lasso, or any other kind. Here I use the 0th order Tikhonov regularization, which meant that the Tikhonov matrix actually an identity matrix, not giving any weight to any particular solution on the other hand. Now what we're looking for is the alpha or the regularization parameter. To find this, you can use an L-curve technique. So actually L-curve is a trade-off between the size of the regularization and the goodness of the fit. So it usually looks like an L, that's why they call it L-curve. And the alpha associated with this corner is what actually you're looking for. So now that you can solve this equation using the Tikhonov regularization, you can pick the best answer to the solution. So back again to the fill. So these are the arrival time. You can see a nice, clean, clear peak, both for the L1 to R4 left number 1 and R right number 4. It is the longest pass that you can see the delta T, the associated delta T for this. This little bump is caused by a flood we had during that time, and this is the shortest path. If you remember, we had to have an angle between the acoustic path and the flow velocity that is smaller than 90 degrees. It is very close to 90 degrees, which means that you're going to resolve a very, very small component of velocity. As a result, you don't see a lot of influence of the flow speed changes on this one. Oops. And here are some of the results of flow visualization. We start from April 16, and then as you can see, because we had those boundary conditions, the stream functions don't go into your boundaries, don't run through the boundaries. And here is the start of the flood. Unfortunately, I guess I don't have the flood itself, but you can actually see that the size of the vectors are increasing, and at the end we had smaller velocity, so you can see that the vectors are smaller, and these are the alpha values. Now comparing the data with ADCPs. So in along channel or along the river, there is a very good conformity between the ADCP and the inversion result, but unfortunately in the transverse direction we don't have that conformity. Also, although we can say that about 98% of the data had an error between plus minus 20% of the ADCPs, which is pretty good. But in the transverse direction, it reduces to 75. Here you can see that 75%. It means that you solve the magnitude of velocity very well, but not the direction. So what causes this anomaly? The answer is that we never introduced the depth, the variation of the depth across the river into our equations. As a result, the equations treat river as, say, a cube, so the depth is uniform all around the river or the area of the target area. This is one reason. The other reason might be that because they were very close, the ADCPs were very close to the boundary, then they captured some of the boundary effect. But here we have very simplified boundaries for the model. As a result, there might be some variation in the direction of the flow. Nevertheless, it looks to be a very promising technique, because it's true that ADCPs give you a lot of details, but they lack of giving you the bigger picture. So if you want to see the bigger picture, this method is going to be very useful. But if you're interested in details, so ADCPs are better. Now I'm moving to the second part of the webinar, which is application of tomography for developing the tidal energy. Tidal energy is very young comparing to the solar power or maybe wind. It is kind of infant if you want to compare it. It is where like the solar power was 30 years ago. So the current challenge in the industry is to find the best sites for installing the turbines. But how we can find the best sites for developing this tidal energy? The answer is that we're gonna figure out where they have the highest currents. But you cannot just do it for short time, because if you put a tidal turbine in the water, it means that you already spend millions of dollars. So you cannot just remove it after, say, a month or two, just because the currents are not as strong, or you have the sedimentation problem, or the topography is changing. So you need something that is cost effective, and a measurement that is cost effective, and also it can be done for long periods of time. So FAT type technology is probably the best answer. So if you're familiar with the Bay of Fundy, you know that the tide currents are very, very strong in there. It's about 1 to up to 3 meters per second, depends on where you are. And the tide range is going to be about 14 to 15 meters. We went to the St. Mary's Bay, to the Grand Passage, which connects the Bay of Fundy to the St. Mary's Bay. The currents are real strong here. It's about 2 meters per second instantaneous currents. And it is a potential site in Nova Scotia for installing the tidal turbines. We had a Zodiac boat. This is Professor Kawanishi, this is Alec Hay, and this is Richard Shield from Dalhousie University, and this is me. So we had the 7 kilohertz transducers, and we had also 30 kilohertz transducers. If you remember, I told you, you have to balance the sound attenuation with the resolution of the sound. So we wanted to know that if 30 kilohertz are going to work, this distance is about 1.5 kilometers, and the water is about 30 meters deep. The tide is about, at that time, was about the tidal range was about 8 meters, if I'm not wrong. So first was to provide some reference data after installing the PAT, the acoustic stations, one in OA, one in OB. We had 30 kilohertz and 7 kilohertz running parallel. So we had a Zodiac boat that you saw, but the currents were very, very strong. As a result, even though we tried to keep the boat in a straight path, but we couldn't. So you see that the transverse fraction, the cross section changes totally. So here we also have a model of the Grand Passage. Is provided by Richard Karsten from Acadia University. So you see that actually we have 2 vortices, one in the left and one in the right, and the temperature of water is totally different during ebb and flow between these two areas. We had also 2 temperature meters. Okay, we also had 2 temperature meters, one close to each of the acoustic stations and measuring the flow velocity, the flow temperature. So as you can see, and OA and OB, the temperature is totally different, especially during the ebb, because of those two vortices. Also, we had a castaway CTD, and we actually measured the flow temperature and salinity in different places across the line. It varies, of course, with the flood and with the ebb. You can see it's totally different. And here are some of the measurements. The arrival times are shown, and shows that they change very well with the tide. And here is the tidal, is the water level, and you can see this is the sound intensity level. It was almost constant, but here are the velocities. If you remember, we only had one acoustic path, so I used the ADCP velocity to extract the flow direction and use it for just ebb and flood, so just two numbers, and I rotated the velocity that measured by FAT along the OA-OB path. So this is a comparison between the ADCP's measurements and also the three arrivals that we have. So in a river, you just have one. I'm trying to get to the previous part. So in a river, we only have one clear peak, which means that that's the arrival time. But in this case, we had three of those peaks. We usually expect to have multiple arrivals when there is when there's vertical structure, as I showed you on the first slide. But here the water is very well mixed. You can see that the temperature is almost straight. Look at the scale, it's about just 0.1 degree difference, or maybe less than that. So the water was very well mixed. So I just wanted to know that why we have always three arrivals. The answer, to find the answer, I use the bellhop model. It's a very robust model for tracing the rays. And the answer was that maybe geometry is important. But as you can see, the arrival times are separated by about 2 milliseconds. But here what we have is about 5-6 milliseconds. And the ratio between the second arrivals and the first arrivals are not really right, because if you look at it here, you can see that almost 40% have one peak and 40% have two peaks, which means that, oops, go ahead, which means that it should be almost, this peak should be around here. So the 2D was not enough. What we did, I used the bellhop in 3D. It is way more complicated than 2D. Here is a bathymetry taken by a sonar that we had. And we took the bathymetry, we mapped the velocity with the bathymetry, and then these dots show where I input the depth of water and the sound speed profiles. To do that, because I didn't have a lot of sound speed measurements in this area, I averaged the entire data I had, all this, come on, all these peaks, all these profiles in the ebb and all the profiles during the flood are averaged together to give you a standardized or normalized flow. So what I did, again, because we had this vortex in here, I assumed that the water temperature in this area is going to be equal to whatever the temperature is at the free port or OB, I guess. And the other thing was that I assumed that this entire area, in this entire area, the water temperature is going to be equal to whatever we had in this station. And then the salinity was also averaged over the ebb and tide, over ebb and flood. So we have the temperature in this region with the constant salinity for the entire region. and I multiplied the sound speed so as it agrees with the sound speed that is dictated by the temperature in each of these stations. Better say. So the results were very nice because we are in 3D. Then the sound is going to be scattered not only in vertical plane that we had about 7,000 rays in about 27 degrees opening angle, but also you can have the sound that goes in the horizontal direction. The horizontal opening angle was 17 degrees with about 3,000 rays, means that the density of rays is very high because it's very, very sensitive. And here is the PDF or probability density function of the arrivals. You can see that every 2 milliseconds you have an arrival. You have 3 strong arrivals. Of course, we had 4th and 5th arrival in the data as well, but because they were not statistically important, I just discarded those data. So and even the ratio is correct. 40% is about 40% is single path, and the rest are with the 40% only single pass, and the 40% have 2 arrivals, which seems quite right. So this multiple arrival is mainly caused not only by the geometry of the bed across the strait, but also because we have some out of plane sound speed scatter. Scatter. Now, I'm just going to introduce what I'm doing right now in the projects that I'm involved. One is a SWAT-UP. It's a multi-beam coherent Doppler bistatic sonar. So bistatic means that the source and receiver are in different positions. If you have an ADCP, you're going to have 4 beams that diverge from each other. And if you want to resolve turbulence, you assume that the turbulence is homogeneous inside this area. Let's say your water is 10 meters deep, then the footprint of the beams in ADCP are going to be 10 meters by 10 meters. So it means that the smallest scale of turbulence that you are resolving is about 10 meters. It means that you are losing or you are missing actually most of the turbulence. So what we did is that we're using, instead of the diverging beam, we're using converging beam. We have fan beams in here, and we have multiple receivers, so we can actually rotate the beam in this area between plus minus 20 degrees. And here are the results. We had it over ripples. So the log law is this one is not really valid because the wake produced by each of these ripples are going to affect the flow. It is the wake law. And this is the MFTOP. It's another instrument we are developing. It's different. And this is the SWAT-UP. So it actually gives you the flow velocity in 2D, in a vertical swath of the flow, which is very, very useful for measuring turbulence near the bed, and especially for the sediment transport. And the other project that I'm currently involved is measuring the upward turbulent flux is induced by the hydrocarbon seeps. You can see here that we are going to grab 2 of our cameras. I apologize for the slow speed. It's about 1,300 meter deep in the water, and we had 2 cameras. In the Gulf of Mexico, we have a lot of oil and methane seeps. These are natural seeps, and there are thousands of them. So no one has ever measured how much gas is released. Methane gas is released. You know that the methane is a very potent greenhouse gas. It is between 20 to 30 times as strong as CO2. It also increases the acidity of the oceans, but we really don't know how much gas is released. So what we did is that we installed ASFM, or acoustic scintillation flow meter, It's another innovative acoustic system. We had an AUV that actually surveyed the whole area for us, and these are the seeps, that major seeps that we found. The flare is actually the seeps, and we picked one seep to do the studies. Here are the ASFM. One is the receiver and the other one is the transmitter. We also had 5 MCATs. They measure the temperature, depth, and salinity of the water in the lower, I guess, 20 meters. And then we also had 3 ADCPs. Here we can see some of the result. And this is the first time that measurements are done. It is multidimensional, and it's a very large project. A lot of institutes are involved. University of California and Georgia University, Columbia University, EcoGec, Oceaneering is the company that provides us with the ship, and the Gulf of Mexico is funding us. So there's a lot of work, but it is very, very interesting. So at the end, I would like to get back to you and see if anyone has any questions. Okay.